Climate changes for many reasons, and one of those reasons is because of human activity. These anthropogenic causes of climate change are primarily due to human activities that increase the atmospheric concentrations of powerful greenhouse gases, namely carbon dioxide and methane. The burning of fossil fuels for energy and transportation is the largest source of CO2 emissions, while methane emissions come from sources like livestock farming and the extraction of fossil fuels. As these gases accumulate, they trap heat in the form of long-wave radiation in the atmosphere, leading to a rise in global temperatures. When analyzing climate data, it is important to understand the difference between correlation and causation. A positive correlation exists when two variables change in the same direction. As one increases, the other also increases. Or as one decreases, the other also decreases. Conversely, a negative correlation is when two variables change in opposite directions. As one goes up, the other goes down. Correlation, however, does not prove causation. It only indicates a statistical relationship between variables. For example, data from Antarctic ice cores reveals a strong positive correlation between global temperature and atmospheric CO2 concentrations over hundreds of thousands of years, with both variables rising and falling together. While this correlation is clear, it does not by itself prove that CO2 causes an increase in temperature. Instead, other evidence is needed to confirm the causal link, which in this case, a causal link is confirmed by other scientific evidence that we will continue to discuss. So let's talk about the effects of climate change and also what we can do about it. When looking at how global warming happens, it's important to understand positive feedback cycles. Positive feedback cycles are self-reinforcing loops in which an initial change in the climate system is amplified, causing even more warming. This accelerates global warming in a non-linear way. Several key positive feedback cycles are at play that you need to know, each contributing to the overall rise in global temperatures. One such cycle involves the albedo effect. As global temperatures rise, reflective surfaces like snow and ice melt. This exposes darker surfaces, such as the ocean or land, which have a lower albedo, which is the measure of how much light a surface reflects. These darker surfaces absorb more solar radiation and emit long-wave radiation, which is reabsorbed by greenhouse gases, causing further warming, which in turn leads to more melting, continuing the positive feedback cycle. Another cycle involves the release of greenhouse gases from frozen reservoirs. The vast stores of carbon in permafrost and deep ocean sediments are normally trapped by cold temperatures. As the planet warms, permafrost thaws, and the previously frozen organic matter decomposes. This decomposition releases large quantities of carbon dioxide and, in anaerobic conditions like in wetlands, methane. Methane is a potent greenhouse gas, and its release traps even more heat compared to CO2. Leading to further permafrost thawing. This is also true for the deep ocean, where warmer water can release stored CO2 into the atmosphere, which then causes the ocean to warm further and release even more CO2. This continues the positive feedback cycle. Finally, an increase in droughts and forest fires creates another positive feedback loop. Rising temperatures lead to drier conditions, making vegetation more susceptible to fire. When forests and peatlands burn, they release massive amounts of stored carbon into the atmosphere as CO2. The loss of these carbon sinks also reduces the planet's ability to absorb CO2, further increasing atmospheric CO2 concentrations. This, in turn, exacerbates the warming that causes the initial droughts and fires, perpetuating the cycle. Boreal forests, also known as taiga, are the world's largest land biome, characterized by long, cold winters, short, mild summers, and a dense canopy of cold-tolerant conifer trees like spruce, fir, and pine. They are found in high-altitude northern hemisphere regions, including Alaska, Canada, and Russia. These forests are vital for regulating the global climate. Because of their cold temperatures, dead organic material does not decompose quickly, so it ends up being stored in the forest as detritus. The vast trees also store a lot of carbon captured by photosynthesis. But because of the stress of climate change, specifically warmer temperatures and less snow, there has been a reduction in primary production in the taiga because of increased drought and water stress. The trees begin to show signs of browning, and this stressed vegetation, combined with drier conditions, increases the frequency and intensity of forest fires. These fires are so severe that they burn through the shallow soil organic layers, releasing what is known as legacy carbon, carbon that has accumulated over decades or even millennia from previous fire cycles and vegetation decomposition. The combustion of this stored carbon then releases massive amounts of CO2 into the atmosphere, further accelerating global warming and pushing the ecosystem past the point of no return. In addition, after fires have taken place, new trees will grow, many of which can be aspen trees that are spaced apart and hold less carbon than fully grown spruce, fir, or pine trees. Due to these reasons, boreal forests are at a tipping point, moving from being carbon sinks, in which they have traditionally stored carbon, and are changing into carbon sources, in which they are releasing more carbon than they store. The melting of polar ice is a significant example of habitat change driven by climate, impacting species uniquely adapted to these environments. In the Antarctic, emperor penguins rely on landfast ice, which is sea ice attached to the coast, as a stable platform for breeding and raising their young from April to January. The early breakup of this ice due to warming temperatures can lead to catastrophic breeding failures, as chicks have not yet developed their waterproof feathers and can die from exposure or drowning. In the Arctic, walruses use sea ice as a crucial floating platform for resting and for mothers to care for their calves between feeding dives. As the sea ice melts and retreats north over deeper waters, walruses are forced to haul out onto land in large, crowded herds. This behavior change increases the risk of stampedes, which can lead to high mortality rates, particularly for young calves. The loss of their primary sea ice habitat also forces walruses to expend more energy swimming longer distances to reach their traditional shallow water feeding grounds. Changes in ocean currents can significantly alter the timing and extent of nutrient upwelling, which is the process that brings cold, nutrient-rich water from the deep ocean to the surface. Warmer surface water, which is driven by climate warming, is less dense than colder, deeper water and therefore prevents vertical mixing. It does this by essentially creating a barrier where the warmer, less dense water sits on top of the colder water, preventing any movement, which can therefore stop upwelling. This stratification prevents essential nutrients, like nitrates and phosphates, from reaching the sunlit surface layer where photosynthetic organisms live. The reduced supply of nutrients leads to a decrease in ocean primary production, as phytoplankton, the base of the marine food web, cannot grow and reproduce as efficiently. Since phytoplankton are the primary producers, a decline in their population diminishes the energy available at the lowest trophic level. This reduction in available energy propagates through the entire marine food chain, negatively impacting populations of zooplankton, fish, marine mammals, and seabirds that rely on this foundational food source. Ultimately, the disruption of nutrient upwelling can lead to a less productive and less biodiverse marine ecosystem. Due to rising global temperatures, many species are experiencing poleward and upslope range shifts to find cooler, more suitable habitats. A poleward shift is the movement of a species towards the Earth's poles, northward in the northern hemisphere and southward in the southern hemisphere, while an upslope shift is a migration to higher elevations on a mountain. This phenomenon is especially evident in the tropical zone montane bird species in New Guinea, where many species have been documented shifting their ranges upslope by significant distances to track their preferred climate as temperatures rise. Similarly, in North America, climate change is causing range contraction and a northward spread in many tree species. As the southern portions of a species' range become too hot or dry, the populations there decline, leading to a contraction of their southern range limit. At the same time, the northern portions of their range become more hospitable, allowing the species to expand into new territories, resulting in a northward spread. This combination of contraction and expansion can lead to a net shift of the species' range towards the pole over time. Next, let's take a look at coral reefs. Rising carbon dioxide concentrations in the atmosphere threaten coral reefs through two primary mechanisms, potentially leading to ecosystem collapse. First, as the oceans absorb more atmospheric CO2, a chemical reaction occurs that increases the water's acidity and reduces the availability of carbonate ions. This process, known as ocean acidification, suppresses the ability of corals and other marine organisms to build their calcium carbonate skeletons, which are fundamental building blocks of the reef structure. This occurs because the influx of CO2 into the ocean reacts with water to form carbonic acid. This weak acid then dissociates into a hydrogen ion and a bicarbonate ion. The increase in hydrogen ions causes the water to become more acidic, lowering its pH. This issue with having all of these hydrogen ions dissolved in the water is that they can react with other molecules, such as carbonate ions. When this happens, it creates more bicarbonate. But under normal conditions, these carbonate ions can interact with calcium to form calcium carbonate, which is an important molecule for organisms to use to build shells and exoskeletons. In these acidic conditions, those carbonate ions can instead interact with hydrogen because more of it is there and it has a higher binding affinity than calcium, meaning there is less overall calcium carbonate available for marine organisms, which negatively impacts their development. Second, increasing global temperatures lead to warmer ocean water. When water temperatures rise above a certain threshold, corals become stressed and expel their symbiotic algae, zooxanthellae, that live within their tissues. This process, called coral bleaching, causes a coral to turn white and lose its primary source of food. While corals can sometimes recover from a bleaching event, prolonged or repeated events can lead to widespread coral mortality. The loss of corals, which are foundational species, results in the collapse of the entire reef ecosystem, as the physical structure and habitat they provide for thousands of other marine species are destroyed. This loss of habitat and biodiversity disrupts food webs and can lead to drastic decline in fish populations and other marine life. Human activity puts a lot of traditional carbon into the air that should be sequestered or stored in other places in the Earth's crust or within living organisms. With that being said, we do have a few ways in which we can take action to remove the carbon out of the air and sequester it again into more natural places. These methods include afforestation, which is the creation of new forests on land that was previously not forested, and forest regeneration, the regrowth of existing forest land. These processes involve trees and other plants absorbing atmospheric carbon dioxide through photosynthesis and storing it in their biomass and the soil. While these methods are beneficial, scientific debate exists regarding the most effective method, with some researchers advocating for rewilding, which is when native species of plants are regrown to promote biodiversity and long-term ecosystem stability. Others argue that plantations of fast-growing, non-native species can offer a more rapid and larger-scale approach to carbon sequestration, as they have the ability to store more carbon at a quicker rate. Another vital method is the restoration of peat-forming wetlands. Peat is a dense, carbon-rich material formed from the partial decomposition of plant matter. This process naturally occurs in waterlogged anaerobic soils in temperate and boreal zones, and also very rapidly in some tropical ecosystems, where the waterlogged conditions prevent full decomposition and allow carbon to accumulate over thousands of years. Restoring these wetlands helps maintain their carbon storing capacity and prevents the release of stored carbon into the atmosphere.